Today's lesson is about the quantum mechanical model of the atom. In our last few lessons, we looked at Rutherford's model, which included the nucleus, but that's not the latest model, and I don't want to leave you hanging. So let's talk about further developments in our atomic model history. We have to talk about the study of light, because we talked about light when we did the Bohr model too, didn't we? Well, one of the things that led into the most recent model of the atom, the quantum mechanical model of the atom, is the debate about whether light is a wave or a particle. To understand whether or not light is a particle, you have to consider the photoelectric effect. Let's have a look at that. This simulation of the photoelectric effect is made by the University of Colorado at Boulder. You can find their website by Googling PHET, and you'll find they have some fabulous animations for lots of cool science things, so I encourage you to check it out. What we're looking at is an electrical setup where we have these brown things are electrodes. It has a metal plate here, which according to this choice is sodium, connected to a voltage meter, and what we're doing is we're shining a light of different color on it. Right now our light intensity is very low. I'm going to move the color of light down here to the infrared spectrum. This is the highest wavelength, so what you see here, 833 nanometers, is a long wavelength, but it's a very low frequency and it's low energy. And as we move down toward the UV light, the wavelengths become smaller and the frequency and the energy are higher. And so what we're looking for, let's turn up the intensity so you can see. This simulates photons, little particles of light, hitting the sodium metal, and we're looking to see if any of them have enough energy to kick off the electrons from the sodium metal. And apparently it doesn't work. So if we increase the intensity, notice the intensity even can go up to 100%. We're shooting a lot of photons. And you would think that if we could shine these photons onto this metal plate long enough with enough intensity, eventually we could make the electrons leave, like when you heat up water on a pan or something like that. But it turns out that it really doesn't work that way. Instead, what happens is that each metal has a particular wavelength of light that makes it effective for ejecting electrons. See, as we change in the light, it's not only its pretty colors, but okay, look at that. We're just now getting into the green part of the spectrum. Now we have electrons flowing, and you can read the current down here on the meter. So it really only worked once we got to high enough energy light. In fact, if we back it off a little bit, let's see at what point. Yeah, 530 nanometers, we're barely getting electrons kicked off at all. Whereas if we go to a higher light, you'll notice that because of the higher energy, more and more photons have the requirement energy to make the electrons be ejected from the metal. And as you can see over here on the side, we can reset it for any different metal. Every metal has its own characteristic energy that's necessary. We have it set on zinc now. Let's take our zinc down to something low. Let's see what's the minimum frequency that will eject it. Look at that. We're all the way through violet light, and none of those colors of light will work for zinc. It looks like for zinc we're going to have to be higher than 200 smaller than 290 nanometers before we get any electrons to flow. Okay, so this is evidence for light being a particle, because you have to have a photon that's big enough to knock the electron off the metal. So we saw in the photoelectric effect that only light of a specific color, and therefore energy, can force a specific kind of metal to lose an electron. the light must have enough energy or be the right color, the intensity doesn't make much of a difference. Albert Einstein was the first to explain this effect by using Planck's formula E equals h nu. That little v there should be a Greek letter nu. It means frequency. The energy of a particle of light, called a photon, strikes an atom, giving an electron sufficient energy to be completely removed from the atom. It has to have enough energy all in that one photon to kick the electron off. If I shine the light brighter or longer, it doesn't really make a difference. If light were a wave, then if you would shine it light enough or long enough, it would eventually work, but it doesn't work. Experiments show only certain frequencies of light can affect the electrons. Some applications of the particle nature of light include photographic film, elevator door light switches, copy machines, and video camera tubes and CCDs. My understanding of CCDs, like you see in the picture there, is that they are kind of the precursor to our technology of digital photography. So let's summarize. For the particle properties of light, we know that light particles interact with single electrons, and that light energy comes in little packets called photons. Those are the arguments for considering light as a particle. However, we have to also consider what you've probably studied before, is that light is also a wave. It has wave evidence. For example, if water waves hit a barrier, what do? They bounce back, they reflect. And light can do the same thing. It travels in a straight line and it reflects when it hits a mirror. Also, light shows constructive and destructive interference. Let's have a look at this too. This animation is from Boston University Physics Department. Very well done, I might add. What you're going to see is two different waves, the red wave and the blue wave, and then we'll see what happens when they come together in the pink wave here. So let's do a constructive animation. Whee! And if we step through that, you can see that two crests are coming together. The red crest is coming to meet the blue crest. And when they get together, they're superimposed and they make a taller crest. That's constructive interference. Let's play it one more time for you. Cool. And then destructive interference occurs when one crest and one trough come together instead of two crests or two troughs. They look like this. So let's step through that one. You can see that one again. Okay, the red is a crest, blue is a trough. Look at that. You can see when they're superimposed, it's not as tall as the red one, not as deep as the blue one, until they pass through each other. And now let's look at destructive interference with identical shapes. That one's really fun. This time the crest and the trough are made the same. So here's where they're coming together. Now look at this. When they're perfectly overlapped, see how they cancel each other out momentarily until they move past one another. Let's play it one more time. Okay, so that's constructive and destructive wave interference. Here are some additional links where you can go to find more information about constructive and destructive interference, and I'll include these on my website as well. Let me show you also a simulation about a ripple tank with water, and so you can observe some constructive and destructive interference. And I want you to also look for what happens when light waves overlap. This is the wave interference simulation from the PHET website, the University of Colorado at Boulder. what you have is a ripple tank. This represents a shallow pan of water, and you can see we're dripping 1 drop of water in. We can vary the frequency of the drips. And we're looking at the patterns that they form, wave patterns. We can also change the amplitude, which changes how tall the ripples are, whether they're tall or short. All right. And the interesting thing that I want you to consider here is if I include, let's use 2 drips. And I want you to notice the interference patterns that occur. You can see here that we have the black and blue stripes are very clear, and then in here we have kind of a fuzzy spot where it represents destructive interference. The waves are canceling each other out here, but on the parts where you can see the stripes real clearly, that's constructive interference. And what else is interesting, let's go back to 1 drip. If we put in a slit, some kind of a barrier with a slit, I want you to notice the interference patterns that form over here as well. Okay, we can make the slit width a little bit narrower. Now, what if we have 2 slits? I want you to notice something interesting that happens. Look how the waves spread out as they pass through the barrier, and we get these interference patterns again as they go through. And it turns out that that happens not only with water, but also with sound and with light. This represents some red light showing on a screen, I guess. We can again change the amplitude, which makes larger, smaller waves. Affects the intensity, I think. We can also change the color of the light to have shorter wavelengths and higher energy if we wish. I kind of like green. Let's stick on green. Okay, but the same thing that happened with the water waves. Let's go ahead up to 2. Have 2 slits. And if we put the barrier in front of the light, again we have wave patterns that develop. As the light passes through the slits, you can see the constructive and the destructive interference patterns that occur here. So we got to look at the ripple tank with the water to observe the constructive and destructive interference, and we looked at the light experiment with the double slits. What you see in this middle picture is when we shine the light through 1 slit, and then this is the picture the way it would look on the wall down here. When we shine the light through 2 slits, we get these bright and dark patterns, where the bright patterns are the constructive interference and the dark patterns are the destructive interference. So this is showing that light behaves like waves. Some applications of the wave nature of light include holograms, like this alien picture here, surveying equipment, checkout scanners, CDs, and video discs. To summarize, light demonstrates interference and reflection. These are the wave properties of light. So back to our question, is light a wave or a particle? We have clear and convincing evidence for either view. So what would you think? Turns out light is both a wave and a particle. Our experiments can reveal either wave or particle properties, but it's impossible to test for both particles and waves at the same time. That's because light behaves as both a wave and a particle. This is known as the dual nature of light. It turns out to be very important in our leading to the quantum mechanical model of the atom. Please look for part 2.